Today we're going to talk about functions calling functions with an introduction to recursion. Recursion simply means a function that calls itself. So first we want to review how functions call one another and how that mechanism and process works, and then we'll look at the special case of recursive functions, which are functions that call themselves. So why are we looking at functions in the first place? Well, functions have a number of properties that help us as programmers. So first, creating a new function means naming a group of statements. This makes your program easier to read and thus debug, which helps us write better programs faster, what everybody wants. Functions also help us eliminate repetitive code by allowing us to make changes in one well-defined place. I name this rule dry, don't repeat yourself, which is taken from the development community. And so you'll see throughout my courses, I often will reference whether your code is dry or not, and this idea of not repeating yourself. If you can look at a piece of code and think of a way to make it shorter, cleaner, more efficient, then you should do so. But make sure the functionality works first, right? So you look at the lens of dryness after your first draft. What I would do when you're writing a program is think of writing a program as sitting down and making the first draft of an English paper, right? A paper you might turn in, a term paper for like a history class or an English class. You sit down, you write your first draft. That's meeting the functionality. That's creating a program that meets the specification that you've been given. That second and final and subsequent drafts, those are where you've looked and you've said, can this be designed better? Can this be more efficient, more reusable? Can it be drier? Functions also allow us to debug individual functions one at a time, so we can test independent units separately, make sure each individual unit is working correctly before integrating them together. This allows us to bound our search space when we find a bug. If you sit down and write 500 lines of code and then you have a bug in it, well, I don't know, I just wrote 500 lines of code, I don't know where the bug is. But if you write 5 lines of code and make it a function that you can test, well, then you're a leg up because you know your bug, if you find it, is only in those 5 lines of code. And so this is a good practice whether you're using functions or not. And finally, the main purpose of functions is for reuse. Once you've written and debugged a function and tested it, the function can be reused infinitely many times, not only by yourself, but by others. That's the idea behind API libraries. Other people have created functions and have given other programmers, us, well-defined ways to access those functions. So what does calling a function look like? What are the mechanics? So here on the left, I have an example function called double DBL, and it simply doubles the parameter x. So the input to the function is x, the output from the function is 2 times x. Similarly, I can compose multiple functions together, as in the case of quadruple or quad, where I take my parameter x and then I double it twice. So I double x and then I double the result of that. So inside of a function, we notice that functions always return to where they were called from, and each function keeps its own variables of its variables. So let me go to a different example. So here, let's walk through this one example. So we start at h3. That's the first call that we can see. And so if we go over the definition for h over on the other side of the screen over here, we can see that when x, which is the parameter name, is 3, as it is in this example here, that we are going to traverse this if-else statement. 3 mod 2 is 1, because 3 divided by 2 has a remainder of 1. And so we know that we are going to return this statement, f of x plus x. Now, I don't know what this statement will return precisely, but I know x will be substituted for 3, as we've done over here. To the right, I'm keeping track of all the function calls that are happening. So I know I'm going to return f of 3 plus 3, but I don't know what that value is because I don't know what f of 3 is. So then the computer, as we would, walking through this by hand, we are going to call f of 3 and look at that. So if I go to the f of x function, I can see if x is 3, I'm going to reduce x by 1, that gives me 2, and return g of 2 plus 1, which I've written over here. Okay, and so we can follow through a series of function calls in this way by taking the parameter values that we have and substituting them in. Okay, so let's keep going. So what's g of 2? If we look over to the left, If x is 2, g of 2 is going to return 4. Hooray! This is the first time we're actually returning a real concrete value. So once we return an actual value and not another function call, then we can pass that value back to each return that came before. So g2 is going to return 4. Then I use that on my return of f of 3, and I can see that's going to return 5. And then I return back again, and that returns 8. So let's look at another example and how this is working behind the scenes. So hopefully by this point we understand the mechanics of how function calls work, and now we're going to understand a little bit more about how the computer supports this. So if we look to the right, we have what's called a stack frame. So if you've done any, you may have heard of this before, but if you haven't, that's fine. A program's memory, it consists of a couple different areas. One is the program itself, the text for the program. And then we have what's called the stack and the heap. So the stack is where all of the function calls go. That's what I'm representing on the right. The heap is all the memory for other uses of the program. So the stack is the call stack. That's going to store information around function calls, the variable parameters that are being passed, and the return values. A heap is for everything else in memory. So any objects, if you've taken Java or learned about object-oriented languages, you may be aware that there's a difference between primitive types and object types. Primitive types are numbers like integers and floats, or decimal points numbers, or strings. These are all like primitive type values, text. Object types would be aggregate types. So for example, if you've worked with Turtle at all, Turtle is an object. If you've created a circle class in Java, that would be an object, or another language. And so objects are bigger entities. In fact, in Python, a file, if you read a file, that's going to be an object. And so those data types are not primitive. You cannot store a single value and have it represent that whole object, because an object contains multiple values. So objects have to get stored somewhere else besides the call stack. They go into an area of memory called the heap. And so the stack can point to the heap, but all the data on a stack frame is related to calls. Okay, so on the right here, we're indicating a call stack, and I have some example functions on the left. So we're going to go through our demo function. We're calling it with x equal to -4, and so then I'm going to traverse through, and I see that, I'm going to return -4 plus f of -4. Well, shoot, I don't know what f of -4 is, so let's keep going. And so what happens is that the call to f is now on the call stack. X is still -4, and it's going to return 11 times g of x plus g of x divided by 2. All right, let's keep going. So what I notice here on the call stack is that the x for the parameter in demo and the x for the parameter in f are distinct variables on the call stack. They are not the same. You could name a bunch of your variables x. I don't recommend that you do so. They're not very good names. But you could. They're not meaningful names, but you could name all of your variables x, and they're still treated independently in the program. And so there's two separate x's running around. The x for our demo function call and the x for our f of x function call. So we need to process each of these calls to g. So I have g of -4. I process this, right? X is -4. I'm returning -1 times x. That I can actually calculate and return back. As soon as I return from the call from g of x, the first g of x, that stack frame disappears. So it comes off the call stack, and then I can proceed forward with the next function call, which is g of -4 divided by 2. And what I want to draw your attention to is that not only are these x's all different memory locations, but they can also vary. So for example, here, this x is not going to be -4 anymore, it's -2. So I calculate this value, I pass it back, and now I can calculate the result of f of x, or f of -4. Once that's calculated, I return the value back, and the stack frame for f is going to disappear, and I'm finally left with the result for demo, which is 42. And once the demo call returns, and returns 42, it also is removed from the call stack. So any values that are used as parameters or returns don't stick around unless you explicitly store them in a variable. And again, this is known as the call stack. So one other thing I want to mention at this point, because it often catches new programmers up, is that there's a difference between returning and printing. And in general, we want to favor returning. Here's why. When I return a value, I have two choices with it. I can store it in a variable here, or I can print it. So with a return, it allows the calling function to have the most options. Whereas with printing, it's a one-trick pony. I can only print, and I cannot assign it as a variable. Because print just displays to the screen, whereas return yields the function's value and allows us to use it elsewhere in the program, whether that's a parameter as to another function call or as a variable that then is used later.